Hi everyone. In Unit 6, thus far, we have been focused on Lewis structures, and we've seen that the octet rule is a very important part of drawing proper Lewis structures. In fact, if you take a look at this picture, even if the atom, for instance, the nitrogen, has a plus charge, it still satisfies the octet rule. You could count it as each line as 2 electrons, 1, 2, 3, 4, 5, 6, 7, 8. This oxygen at the very top, at the 12 o'clock position, it's neutral. It satisfies the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen on the right, it is negatively charged. It still follows the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. But even though this octet rule is prevalent and super important, there are some exceptions. And in this video, we are going to look at incomplete octets, okay, where we have less than 8 electrons in the valence shell of a central atom, and hypervalent, or you might know this as expanded octets. Okay, I want to go over a couple examples, and the first example of a molecule that doesn't obey the octet rule is the incomplete octets of several groups. We're going to start with group 2A, and I'm talking about the central atom. So if the central atom is in group 2A, we could have a central atom that is beryllium, for instance. Beryllium is a metal, and it can covalently bond, or just depends on its partner, but we'll call it ionically bond to, let's say, 2 fluorines. So this molecule is BeF2. And if we use some of the steps that we've looked at before when drawing proper Lewis structures from chemical formulas, we should count up the valence electrons. And it's neutral, and beryllium has 2 valence electrons plus 2 fluorines that each have 7 valence electrons. That is 16. Okay. What was the trick? You put the central atom, and you put the outer atoms around it bonded singly to that central atom. And then we fill in the lone pairs. The reason why I put 3 lone pairs around a fluorine is that I know that it brought 7 valence electrons to the bonding party, and one of the electrons is this one here, and the other 6 are in non-bonded lone pairs. Let's double check that we have 16 electrons. If not, you remember that we put the extra electrons on the central atom. 2, 4, 6, 8, 10, 12, 14, 16. So this is a check. Okay. Beryllium can have only 4 electrons around it. So this is called a incomplete octet, and that is okay. Okay for group 2A. Let's look at group 3A now, boron. Let me start you off with the chemical formula of a compound that's pretty popular in organic chemistry. Borohydride, BH3. Don't worry about the name. It's not following the rules that we've learned. It is a compound made out of, well, it is a covalent compound. And let's see, how many valence electrons does this have? Boron has 1, 2, 3 valence electrons. So 3 plus 3 hydrogens times 1. 1 valence electron per hydrogen. That's a total of 6. B in the middle. Again, the shape or how you draw these lines and their angles are not important right now. Okay, I just tend to spread them out on paper. And now we count 2, 4, 6, and we're done. So let me just say here that this is also an incomplete octet, and that's okay for group 3, 3A. I'm using this notation up here, 3A. Okay. Another one that I want you to try is aluminum trichloride. Using the nomenclature rules that we've learned before, we can name this. This is this is boron trihydride. This is aluminum trichloride. And back here, beryllium fluoride. Aluminum is right underneath boron. 3 valence electrons. We have 3 chlorines. 3 times 7. 21, 22, 23, 24. 24. Central atom. Singly bonded to the outer atoms. Understand that chlorine brought 7 electrons to the bonding party. There's 1 already that's making the covalent bond. 1, 2, 3, 4, 5, 6, 7. If we count the number of electrons for this portion of the molecule, we have 8. 2, 4, 6, 8. But we have 3 of those situations. So that's 8 times 3, 24. Oh, definitely make sure you draw your lone pairs because that's what your grader will be counting. We're done. We don't have any extra electrons, so we're not going to put any electrons on the central atom. Again, this is an incomplete octet for aluminum. Okay, not for the chlorine. Chlorines are good. But the aluminum has an incomplete octet, and we should know that for atoms, central atoms that are in group 3A, that's fine. All right, so those are your examples for the incomplete octets. Incomplete octets. Let me go over a couple more central atoms where you could have more than 8. Okay, I call that hypervalent, but again, some of you know this as expanded octet. Let us title this expanded octet. And I do like the term hypervalent. So those two are equivalent because we aren't making an octet. It's kind of a weird name where you could have expanded octet. Let's just call it hypervalent. Valent meaning valence, right? Valence electrons, and you have more than what you expect, more than 8. The first example is a polyatomic ion, Cl03, and you know this as chlorate minus. Right, let's start from scratch. Let's say your professor gives you your chemical formula. It is a polyatomic ion. The name is chlorate. But how many valence electrons does this have? The number of valence electrons is, let's see, 7 plus 3 times 6 for each oxygen. But it's negatively charged. You have to add an electron. 18, 19, 26, 26 valence electrons. Central atom is chlorine. We talked very briefly about electronegativity. It follows the same trends as electron affinity. And it was a very quick and subtle rule that I mentioned before. If you're wondering what is the central atom, put the one that is the least electronegative. As a guide, fluorine, you should know this, and you should know this from memory. Fluorine is the most electronegative atom. Fluorine is the most electronegative atom. The noble gases really don't count because they don't want to gain an electron. And they don't participate, for most of these, they don't participate in bonding. You only think about electronegativity when we think about bonding. Fluorine is most electronegative. Oxygen is second most. It follows the same trend as electron affinity. Increasing electronegativity goes to the top right, but don't include the noble gases. The central atom, again, you should put the less or the least electronegative atom in the middle. Remember your trick? You're going to put single bonds to the outer atoms. Okay. Now, the trick for polyatomic ions is to go ahead and satisfy the octet rule for all the outer atoms. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So each oxygen has 3 lone pairs and a bond, and that satisfies the octet rule for each of these oxygen atoms. Now we got to double check if we have the right number of valence electrons, and we don't. You see here that we are too short, DWO, because we have 24 total so far, but we need 26. Let me double check my count. 7, 3 times 6 is 18. 25, yep, we should have 26. And the rule is, if you need to add more electrons to get up to the valence number of electrons, you put them on the central atom. So that's a check. Now, what's not a check yet is us considering the charge. We have no charge so far. Okay. Hopefully you remember that to get the formal charge is number of valence electrons minus sticks plus balls. So there's 6 minus, there's 1 stick, and then each electron counts as a baseball, and that equals negative 1. So each of these oxygens is negative. But what about the chlorine? Chlorine has a valence of 7 electrons minus 3 sticks plus 1, 2. So this is 7 minus 5. This equals plus 2. And remember, when you do the charge, it's the number first, then the sign. It's just habit that I circle the charge because I don't want the grader to confuse a marking as a dot if I really want it to be a charge. Okay. And that's 2 plus. Now this seems like it follows all the rules, okay? And chlorine is also an octet. But a more important rule that you don't want to violate is there should be no atoms that have a plus 2 or a minus 2 charge, or a plus 3 or a minus 3. The charge should always either be neutral, which is the best, 1 minus or 1 plus. So we got to take care of that. Yes, we are going to violate the octet rule by doing what? Well, we could get this down to plus 1. Okay. See, the goal of this is to minimize not only the number of atoms that have a plus 2 charge, okay, but really it's to minimize the atoms that have a charge at all and try to get most of them to neutral, okay? So by moving these 2 electrons, we'll make this oxygen neutral, the one on the left. Okay, do you see how I'm taking my purple arrow and I'm drawing the result? This is chlorine. But that chlorine, right, would have a what charge? It would have a 7 minus 1, 2, 3, 4 sticks and 2 baseballs. 7 minus 6 is plus 1. Okay. We can get rid of that plus 1 by moving another lone pair. See, do you see what that accomplishes? I get rid of the charge for chlorine, but I also get rid of the charge for this oxygen. And we have this. Okay. Right now, the charge on chlorine is neutral. Right? 7 minus 5 sticks plus 2 baseballs. So that's neutral. So we're not going to move another lone pair. Chlorate looks like this. Chlorate looks like that. Okay. And we could double check this chlorine right here. It's 7 minus 5 sticks plus 2 balls equals neutral. Not only that, we know that chloride has a net negative charge, so this molecule has a net negative charge. This is preferred. And not only is it preferred, this is the answer. That is the Lewis structure for chlorate. Now, some people might have said, well, I could get this oxygen to be neutral by moving this lone pair down. And that seems reasonable. This is a very interesting example. So now all the oxygens are neutral. But do we still have a chloride that has a negative charge? We might possibly do. This chlorine has 7 valence electrons minus 6 sticks plus 0 baseballs. No. How many sticks do I have? 1, 2. Oops. We have 2 baseballs. See, nothing happened to this lone pair. So this is 6 plus 2. That equals now minus 1. So yes, you have a negative charge on the chlorine. Why is this not as good? This is a rule that I probably have not discussed yet. So this is not as good. It's okay, right? It's definitely better than this up here. It's not the preferred one, and I'll get rid of this preferred. This is the answer, and this is not as good. It's not as good because if we have a choice between putting a negative charge on an oxygen or chlorine, you want the negative charge on the more electronegative atom. Is more than chlorine. That's with all things being equal, right? All the oxygens satisfy the octet rule in both cases. Both structures have the right number of valence electrons. Okay. Both cases minimize the number of atoms that are charged. The only difference is we have the negative charge on 2 different atoms. And if you have that, the only difference, choose the one that has the negative charge on the more electronegative atom. Electronegative means that it can accommodate the charge, the negative charge, better than an atom that is less electronegative. Okay. That example is ClO3 minus. Let me do another example. The next example is going to be PCl. Let's do a positively charged compound. Pcl4 plus. Draw the Lewis structure for this. Oh, by the way, I forgot what the point of this was. expanded octet or hypervalent. It is okay for chlorine to be hypervalent because chlorine is in the third row, and you're going to say that it has electrons in the third shell, n equals 3. But what other orbitals are in the third shell? It's not just the s, and it's not just the p. If it was just those two orbitals, types of orbitals, you'd have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in that valence shell. But you understand that the d orbitals start at shell equals 3. So you could say that these third period atoms, they have access to 3d orbitals. And let me write that down before we do this example here. Let me write it above here. The third period atoms, and I'm going to start with, most examples where you have a hypervalent situation, it's going to be P, S, Cl, or anything below that. So, actually, I'll include silicon as well. Third period atoms, Si, P, S, Cl, okay, can be hypervalent, meaning that you don't have to follow the octet rule. You could have more than 8 in the central atom's valence shell. Hypervalent. Okay. I wanted to put down that rule because we have phosphorus. Okay, let's tackle this example. Phosphorus has 1, 2, 3, 4, 5 valence electrons, plus 4 chlorines that each have 7. This might be one of our first examples of a molecule that has a plus charge, a net positive. We lost an electron to become net positive. Let's see, 28 plus 5 is 33, minus 1 is 32 electrons. You have your central atom, P. It is less electronegative than chlorine because it's to the left of it. Remember, electronegativity increases from the bottom right to the top left. So as you go across the period, chlorine is more electronegative than sulfur, is more electronegative than phosphorus. We have the 4 chlorines, and again, the trick is to make them all single bonds at first. We have, the next trick is to make each of the outer atoms fulfill the octet rule. Next, you want to count the number of valence electrons and see if you satisfy the total. 2, 4, 6, 8 for each bond to chlorine, and then we have 4 of those. So 8 times 4 is 32. We're good with that. Huh. And this one, it looks like, oh no, we have a plus charge somewhere. So we're not quite done. Where's the plus charge? The chlorines are all neutral. Let's check out the phosphorus. Phosphorus has a valence of 5 minus sticks plus 0 baseballs that equals plus 1. So phosphorus has a positive charge. Let's see. I actually wanted to pick an example that has a lone pair on the central atom. So actually, this phosphorus satisfies the octet rule already, and you should stop right there. We only have one atom that's charged. Phosphorus satisfies the octet rule. It doesn't have to be. It could be hypervalent, but in this case, it doesn't need to be. Doesn't need to be. Let's see this example here, Pcl5. neutral. 5 valence electrons for phosphorus, and now we have 5 chlorines times 7, and it's neutral. This is 40 valence electrons. Ah, okay. So this is the one that's going to be hypervalent. Phosphorus, we have 5 chlorines. Definitely phosphorus has to be hypervalent. The next step is to make each outer atom satisfy the octet rule. Okay. Chlorines all satisfy the octet rule. Let's make sure we have 40 electrons. For each bond to chlorine, we have 2, 4, 6, 8, but we have 5 bonds. 5 times 8 is 40. Let's check the charge, especially for the central atom. Phosphorus has a valence of 5, minus 5 sticks, plus no baseballs, neutral. And yeah, Pcl5 is neutral. This one does show that phosphorus is hypervalent. Just like chlorine, in this case, is hypervalent as well. All right, so those are a couple of examples. There's many more. A lot of your polyatomic ions, you'll have a central atom that's hypervalent, like sulfate or phosphate. Okay, and then we have an unusual one, chlorate, where a halogen is a central atom, and this halogen, normally you would think a halogen has only one bond. Okay, but in this case, since chlorine can be hypervalent, we have this example, and it happened to be, we made chlorine hypervalent, right, to avoid chlorine having a 2+ charge. Okay, and again, this is the best Lewis structure for this chemical formula. Okay, if you need practice, let's do perchlorate. Okay, and you'll do this at home. Draw the Lewis structure for perchlorate.